Okay, in this lecture we're going to put together some ideas that will allow us to graph a polynomial function. The ideas are from our first sections on how to find zeros, which are in actual fact the x-intercepts. Right, so we're going to look at using the rational zeros theorem, if you like. Okay, so that's our first step we're going to use to graph a polynomial function. Next, the y-intercept, of course. This occurs when x equals 0, so that shouldn't be too hard. Next, we're going to check the sign. That means whether it's positive or negative in the intervals formed by the x-intercepts. So that gives us an idea whether it's above or below the x-axis in those intervals. Okay, and then we're going to do the end behavior. Of course, what happens when x approaches infinity and x approaches negative infinity. Okay, so that will be depending upon what the leading term is and its degree and whether a is positive or negative. And then plot any extra points as needed. Okay, so let's start with number 1. Now the rational zeros theorem for this particular one here is going to say that I need P over Q, right, which of course is 8 over 1. Now, what we're going to look at, of course, is we need factors of 8, which is plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. These are factors of 8, which is our P, of course. And of course we have a is equal to 1 here, which is positive. Let's keep that in mind. And so we need plus or minus 1, which is our factors of 1, and that's our Q. Alright, so what we need then is to try a few things here. And if we try 1, for example, and that one's a pretty easy one to try. I'll put in 1 cubed. Well, we can do a, if I put a 1 and we have our polynomial. I put 1 here, I get 1, I get negative 2, I get negative 2 here, and I get negative 8, and I get negative 8, and bingo, I've got the first one. Well, that was helpful. Okay, so since we have that first one, we have, this means of course that x minus 1 is a factor. Alright, now we have a cubic, so that's as far as we need to go. Our function then can be written as f of x equals x minus 1 by this quadratic, which is x squared minus 2x minus 8. Now let's see if we can factor that some more. Factors of negative 8 add up to negative 2, so it looks like a 2 and a 4, doesn't it? And a 2 and a 4, probably a negative 4 and a positive 2, and that works. And so here's my zeros, 1, negative 2, and 4. Okay, so that's going to allow us then to plot those as the x-intercepts. They're going to be 1, 0, negative 2, 0, and 4, 0. Right, so that's number 1 done. Number 2, the y-intercept. Right, now that comes from an x is equal to 0, so f of 0 here is going to be equal to, when we put 0 in here, 0, 0, 0, and an 8. So of course our y-intercept is 0, 8. Okay. Right, number 3, we're going to check the signs. We're going to do that when we start graphing. Now the end behavior. Okay, well let's do number 3 will be on the graph. And number 4 is going to be the end behavior. As x approaches infinity, now let's have a look here. We have a is equal to 1, which is positive. And the degree, so what we have here is a equals 1, which is positive, and we have n is equal to 3, which is odd. Okay. Alright, now if that's the case, alright, we can check here what happens to the function. because we're looking at an x cubed, all right, x is going to where? So as x goes to positive infinity, this is going to go to positive infinity. As x goes towards negative infinity, f of x is going to go towards negative infinity. All right, so let's do a rough sketch of this. All right, here's our axes. Make sure you label those. All right, so our intercepts are 1, 2, 3, 4. So there's 1 there, and we have -1 and -2 and -3. So there's -2 there. All right, now let's check the signs in between here. Okay, and so we can do this down here on the graph. Let's have a look. So -3, for example, and I'm going to use the factored form because it makes it so much easier. -3 will make this all -4. By -1 is a +4. By a -7 will be a -28. So it's going to be negative this side. And that, of course, is verified by the fact that as x goes towards negative infinity, f of x goes towards negative infinity, so it's going down here. So clearly, it's going down this direction. Okay? Remember, this is only a sketch. Okay? We do it as accurately as we can. Right, now what happens if I put -1 in here? All right, well, -1 will give me a -2 by a +1, which will be -2, by a -5 will be a +10. So somewhere up here it comes up, and then of course it must come back down, and it goes through 8. Okay, and so it's coming down here like so, right, because it's positive in this interval -2 to 1. Right, now it's come down through this one here. Now what happens if I now have 2? If I put 2 in here, I get 1, and 4 is 1 times 4 is 4, times -2 is going to be -8. So in here it's negative, so it's coming down here to -8 and turns around somewhere and comes back up. And that's verified by the fact that as x goes towards infinity, f of x goes towards positive infinity, and so there's our end behavior. All right, right there, and this is my function, f of x equals x cubed minus 3x squared minus 6x plus 8. And that's the procedure. One, find the x-intercepts, which of course are the zeros for the function. We need the rational zeros theorem to do that in synthetic division. That's probably the most work in here. Okay. Then we find the y-intercept. That's probably the least work. On the graph, we find the intervals where the zeros, what the intervals the zeros make, and then we check the signs in those intervals, and we then look at the end behavior, and that should line up with the signs that we've found on the graph here. Right, so that's how we institute this graphing technique 1 through to 5. We could put some extra points on there if we wanted to. Okay, for example, -1, 10, I believe, was one of the points that we had there. Right, and down here we had 2, -8. Right there. All right, so that's how we do that. Now the next one helps us to try and locate a 0, and will help us with the rational zeros theorem, or when we need to approximate a 0. Let's suppose that f of x defines a polynomial function with only real coefficients. Okay, so there's only real numbers in front of the variable x to whatever exponent, and if the real numbers a and b, all right, we have f of a and f of b are opposite in sign. So maybe f of a is positive, f of b is negative, or vice versa. F of a is negative and f of b is positive. Then clearly, if you think about that, all right, and our function, all right, and here's our a and here's our b, for example, then it comes from here to here, then you can see that here our f of, I'll actually do it up here. Here's our f of a, right here, and you can see that this is positive. And if I come down here, come across, here's f of b, and that's negative. So clearly it crossed from positive to negative somewhere, so it must have crossed the axes. Alright, alternatively, of course, we could have this deal going on, right, where we have this going up like this. Right, and so this is f of b here, and this is f of a here, and this one here you can see is positive, and this one here is negative. So again, it's changed from negative to positive. As long as they're opposite signs, then the intermediate value theorem says that obviously there's some value c which is 0 in here. Alright, and you can see that this is our value c here, and this is our value c here. So the function is 0 somewhere in here, and c is the 0. Okay, alright, so let's use synthetic division intermediate value theorem to show that there is a, show that the polynomial 3x squared minus x minus 4 has a 0 between 1 and 2. We don't really need synthetic division, but if you have a larger polynomial, then it certainly does help. So what if we use 1 here, and of course we have 3, negative 1, negative 4. Notice that if I bring a 3 down, I end up with 1, 3 is 3, I end up with 2, 1's 2 is 2, add I get negative 2, which is less than 0. Now if I use 2 here, and I have 3, negative 1, negative 4, I bring the 3 down again, so this gives me 6, this gives me 5, gives me 10, and then when I add I get 6, which of course is greater than 0. So notice that f of 1 is less than 0, and f of 2 is greater than 0. So they change sign. So by the intermediate value theorem, there is a number c in the interval 1, 2, where f of c is equal to 0. Alright, so there's at least one, alright, there is at least one 0 between x equals 1 and x equals 2. Okay, and that's how we use the intermediate value theorem.